In this lesson, we're going to introduce the concept of a gradient. Before defining a gradient, I want to give you an intuitive feel for what they actually are. To begin with, let me go ahead and draw two hills, one with a really steep gradient and then one with a really shallow gradient. Now, if you were given a choice to either walk up this mountain or this mountain over here, I think it would be a wiser choice to pick this mountain on the left. Despite the fact that this mountain is actually taller than this one, it's going to be much harder to climb up this really steep slope. So we would say this mountain is really steep and this mountain is a bit less steep. So gradient is just another word for steepness. Therefore we can say that the mountain on the right has a very large gradient and the mountain on the left has a much smaller gradient. In order to actually measure the gradients of the mountains, imagine we started at some fixed point on both of them. Then, on both mountains we go across by some fixed amount, and then we check how far we have to rise to get to the surface of the mountain in both cases. So as you can see, on the mountain on the left, when we go across by some amount, we don't have to go up very far. But on the mountain on the right, when we go across by the exact same amount, we have to go up much further to get to the surface of the mountain. Notice that it doesn't really matter where on the mountain we started, because the steepness of these two mountains doesn't really change. Now of course a real mountain may actually be steeper in certain places than it is at others, so the steepness can actually change at different places on the mountain. So this actually gives us a useful definition for what a gradient should be. A gradient is how much you have to go up or down every time you go across by some fixed amount. Now gradients can do way more than just measure the steepness of a mountain. For example, let me go ahead and show you the profits of two businesses over the last 2 years. Now when you look at the profits of both business A and business B, you notice that business A has consistently made more profit than business B for the whole of the last 2 years. However, if I asked you to predict the future, if I asked you within a year, who do you think is going to make more money, business A or business B, wouldn't you be inclined to pick business B? The reason I'd pick business B is because I can see that business B has been increasing its profits every single day, and business A has been decreasing its profits every single day. We can be a bit more precise about this as well. If we treated business B's curve almost like it was a mountain, we can see that we'd be climbing up the mountain. If business A's curve was like a mountain, it looks almost like we're climbing down that mountain. So in a sense we're saying that business B's profits are increasing and business A's profits are decreasing. If this trend is to continue, eventually business B will overtake business A. Now just like we did on the mountain, we can go ahead and draw a triangle to estimate the gradients of both business A and business B's profits. Now we're ready to be a bit more precise about this. You can see that I've picked some day in the past for both businesses, and I've drawn their profits on that particular day. If we compare it to the amount of money they made today, you can see that business A has actually made less money than they did that day, and business B made more money than they did that day. Now since it's possible to capture the fact that business A's profits went down, it's also possible for gradients to point downwards as well as upwards. Now let me go ahead and make some space for one more scenario. Now we've got a car on the road here, and I want you to imagine that we've moved the car forwards and backwards along the road as I've shown. Now let's say we wanted to actually record the position of the car at any given time. Now let's let the car do the drive again, but we'll also record its position as we go. Now just like we did for the mountain and the business, this time we can actually ask a different question. We can ask, when is the car covering the most distance in the minimum amount of time? If you're familiar with this concept, we're actually asking, when is the car going the fastest? It actually turns out that the car is going fastest when the size of its gradient is the largest. This actually matches up with this section over here, which was actually the point where the car was moving fastest in the animation. In fact, if we look carefully, we actually notice that the slope tells us quite a lot about the movement of the car. We noticed that the car was going forwards over here, and then it stopped momentarily. Then it started reversing and stopped again before it took off to go as fast as it could. Then at the end it stopped and reversed all the way back to the starting line. Now all of these things that I've written can be captured by little line segments that we can draw on the graph. Now the gradient over here points up, so it looks like the car was going forwards. The gradient over here is also pointing up, but it's pointing much higher, so the car was going much faster. These three places over here look kind of like peaks or valleys on a mountain, and at these places it looks like the car was stopped for a moment. And at these two places, since the slope is downwards, you can see that the car was reversing. Now since the slope over here is actually much larger, you notice that the car was also reversing faster at that place as well. So I hope I've given you a little bit of a taste for why we would care about studying gradients. I could really be here for the rest of the day telling you about all the applications, but instead I think it's better that we just move on and you discover them for yourself as we go on. So on the next page, I'm going to go ahead and actually show you how we go about measuring gradients properly. Now to actually make proper measurements of a gradient, you're going to need some kind of coordinate system. So let's go ahead and actually draw on our curve onto some coordinate system first. Now I'm going to go ahead and randomly pick 2 points on this curve. Now I'll go ahead and label the first point P1, and it can have coordinates x1, y1. And now we can go ahead and label our second point P2, and it will have coordinates x2 and y2. Now it turns out that the curve itself is not actually that important, and all we really need to care about are these 2 points. So let me fade the curve out just a little bit. Now we can actually draw the triangle beneath the points P1 and P2 that indicates how far we've moved to get from P1 to P2. Now because the x and y axis are perpendicular to each other, then we can immediately see that this triangle is also a right angled triangle. Now as we said before, the gradient measures how far you go either up or down once you've traveled across a certain distance. Therefore, I'm going to define change in x to be the distance you've moved in the x direction, and change in y is going to be the distance you've moved in the y direction. Now this tells us that the gradient between P1 and P2 is captured by the numbers change in x and change in y. Now just to make it clear, this little triangle over here is the Greek letter delta, and it usually just means change in. Now it is actually possible to write out change in x and change in y in a coordinate like this, but it turns out that it's not so useful to do that in every case. For example, if I just gave you 2 coordinates containing change in x and change in y, in the first example we move across by 3 and up by 2. In the second example we move across by 5 and up by 7. Now by just comparing these 2 coordinates, it's not actually clear which one has the steeper slope. So instead, I'm going to give you a slightly different definition that lets you easily compare gradients just by looking at a single number. We're going to define the gradient between 2 points with the letter m, and it's just going to be defined as change in y divided by change in x. Now one of the immediate downsides of doing this is that you can't represent vertical gradients anymore. So for example, in this coordinate over here, we haven't moved across but we've moved up by 1. In the second case we haven't moved across but we've moved up by 6, and in the third case we haven't moved across but we've moved up by 2. All of these cases would break if we tried to find m because you'd end up dividing by 0. For example, for this one you'd get 6 divided by 0, and as we know that's just not defined. So this just means that we can't represent vertical gradients. I've drawn a little picture of this to show you what I mean. You can't have gradients that go completely vertically upwards. Now so far we've been a little bit too general, so let me go ahead and show you how to find the gradient between 2 actual points. Now suppose you had these 2 points over here on an xy plane, and you wanted to find the gradient between them. The first thing I'd do is to draw the triangle below them. Now let's think about how far you'd have to go in the x direction to get from this point over here to this point over here. You can see that you'd have to move 2 units right to get to the origin, and then 5 more units right to get to the base of the triangle. This means that you'd have to move 7 units from the left all the way to the right. Now since you're starting at a height of 3, and you want to get up to a height of 6, you just have to move up by a height of 3. Now in this case, since change in y is just 3, and change in x is just 7, we can immediately write the gradient as 3 over 7. Now if we wanted to, but we definitely don't have to, we could actually represent the gradient in terms of these points over here. If you look carefully, you notice that this height over here can just be found by starting with 6 and then subtracting off 3. Now despite the fact that our x-coordinate is negative, the exact same trick also works with the x-coordinates. You can just see that the 7 over here is the same thing as 5 minus minus 2. And this means that we can also write the gradient as 6 minus 3 divided by 5 minus minus 2. And now, given this, you actually already know how to find the gradient of any 2 points. So just like we did on the example, we can say that change in y is the same thing as y2 minus y1. And then we can also say that change in x is the same thing as x2 minus x1. And this actually allows us to rewrite the equation of this gradient in terms of the coordinates of our points. Now you could just treat this as a formula that you use and don't think about, but I always like to draw this triangle because it shows me what's going on. Now the great thing about actually writing the gradient like this is that it allows us to compare different slopes by just looking at the value of the gradient. Now in this example, we move across by 1, but we go down by -3, which immediately means that change in y over change in x is just -3. Now in the next example, we move across by 1, but we go down by 2. This means that the gradient is just -1. Now in the next case, we move across, but we don't actually move up or down at all, and this means that the gradient of a horizontal plane is just 0. Now for this situation, every time you walk across by 1, you also rise by 1 as well, and this immediately tells us that the gradient is just 1. Now in this final example, when you move across by 1 unit, you actually have to climb by 3 whole units, and that means the gradient is 3. Now therefore, you can also think of the gradient as the amount you rise divided by the amount you run. In the cases where you go down, you're actually rising by a negative amount, and therefore the rise divided by the run is a negative number. Now as a final bonus, let's actually bring back the problem we were looking at before, to actually see if we can find a way to find the angle of the slope from its gradient. Now as we said before, this triangle over here is just a right angled triangle, and therefore we can actually go ahead and find the angle that the slope makes to the base. If you remember SOHCAHTOA, I want you to remember that the tan of theta is just going to be 3/7 on this triangle. Now if we just go ahead and take the inverse tan or arctan of both sides, we can actually isolate theta. Now I just want you to notice that 3/7 is the exact same thing we got for the gradient. This immediately tells us that tan theta is the same thing as the gradient. If we just wanted to find this angle in degrees, we could just type it into a calculator. Now just remember that your calculator may have a different way of writing arctan, which is the tan to the power of -1. So just plug in the correct function based on the calculator that you have. And now with this, we've actually completed our example. And now we can actually repeat the exact same procedure on this triangle on the left. Let's start by marking out the angle theta. Now from this, we immediately notice that tan theta is just change in y divided by change in x. But as we said before, change in y divided by change in x is the same thing as the gradient, so we can replace this in this formula over here. And now we actually have a general relationship that we can use to convert between angles and gradients. So just to quickly summarize this lesson, we've shown you that the gradient is just the rise divided by the run. And we can use the gradient as a very useful way to compare different slopes. And finally, there's a very simple relationship between angles and gradients. And with this, we've actually completed our discussion on the gradient.